Hello, everyone, and thank you for taking the time to join us today for this exciting webinar being brought to you by Syntica. My name is Sadi, and I will be your host for today's webinar. So the talk of today is titled Enhanced Ultrasound Vector Flow Imaging, or VFI, using multi-angle plane waves. Today's webinar will be given by Dr. Yang, who is an accomplished engineer and researcher with a BS in Electronics and Engineering from the National Chiao Tung University, and an MS and PhD degree in Electrical Engineering from the National Taiwan University. He began his career at the Industrial Technology Research Institute before serving as director at Coretronic Corporation, later which he joined S Sharp Corporation in 2011 as CTO and CEO. He spearheaded the development of cutting-edge ultrasound technologies, including high-frequency preclinical imaging systems, research-oriented array platforms, portable ultrasound devices, and ultrasound reflection tomography. He furthered his expertise as a visiting scientist in the Department of Bioengineering at the University of Washington in Seattle. Currently, he is an associate professor at the National Yang Ming Chiao Tung University, where his research spans real-time ultrasound systems, beamforming, Doppler flow imaging, cardiac elastography, contactless ultrasound biometric detection, underwater imaging, and photoacoustic imaging. Before we begin, I'd like to briefly mention a few housekeeping items. We anticipate that Dr. Yang's presentation will be about 40 minutes, which should leave us time for questions near the end. Please submit your questions in the Q&A dialog box throughout the presentation, and we will go through them at the end of the session. We will also create a transcript of the questions we do answer during the session, as well as those we may not have a chance to address. And this transcript will be made available afterwards. And please note that we are recording today's session, so if for some reason you lose connection or can't hear everything clearly, you will have access to the video file afterwards. So without further ado, I am pleased to turn this over to Dr. Yang for today's webinar.
Yeah, thank you for the introduction. Hi, everyone. Thank you for having me in this webinar. So today I'm going to talk about state-of-the-art I cannot share. I want to talk about state-of-the-art broad imaging in medical ultrasound. So I expect what you can learn from this webinar is as follows. Number one, you can learn about the clinical Doppler ultrasound and its limitations. The second one, you can learn about the state-of-the-art vector flow imaging techniques. And the third one, I want to introduce my current research, trying to overcome the current VFI image, try to improve the current VFI image. We leverage the ultrafast image and the speckle-tracking into the VFI framework. The last one is I want to share the experimental results, especially for the human scan using the research platform in my lab. So let me give you some background about the medical ultrasound. So the medical ultrasound imaging system use 1 to 18 megahertz frequency to do the imaging. There are a bunch of a lot of imaging modes in clinical ultrasound, but they can be divided into two categories. One is brightest mode, we call it B mode, which can provide structure information. The other one is a Doppler mode, which can provide the motion estimation. So there are primarily two applications for Doppler. One is the vascular and cardiac chamber for blood flow imaging. We have a color Doppler, we have spectral Doppler, and VFI. The other one is we can estimate the motion of myocardium to quantify the deformation of the myocardium. So in this case, we have a tissue Doppler imaging and the transverse imaging. So I want to talk about the advantages of ultrasound over other imaging modalities. If we look at this table, you can find the MRI and ultrasound can do a real time blood flow imaging. But the ultrasound has advantage over MRI in terms of mobility and the price. So I expect that you must be familiar with the Doppler effect from your high school physics class. You know the ambulance, right, is approaching you. When the ambulance is approaching you, you can hear higher frequency than when the ambulance is away from you. So this frequency shift that we call the Doppler shift is directly related to the velocity of the ambulance. If we can estimate this Doppler shift, in principle, we can estimate the velocity flow. So the principle of Doppler ultrasound is coming from the Doppler effect. So you can see for the ultrasound, we transmit a focus beam into the vessel. This transmitted signal can be a continuous wave, like the waveform shown here. Also can be a pulse wave, depending on your applications. When the receiver can receive the echoes from the vessels, and there is a Doppler shift that we call it FD. FD is directly related to the velocity, but this velocity is only in the axial direction, which means the direction is parallel to the beam direction. So for the Doppler principle, we can only detect this one-dimensional direction, one-dimensional velocity component. We cannot detect the lateral velocity component. So this is a limitation of the conventional Doppler. In clinical ultrasound, we have a color and power Doppler that can provide the two-dimensional flow imaging. Color Doppler, in color Doppler, we use the velocity, magnitude, and direction. We color code these two information. The red color means the flow direction is approaching the probe. The blue color means the direction is away from the probe. The velocity magnitude is related to the color intensity. On the other hand, the power Doppler only provide the Doppler energy. They don't provide the velocity magnitude or direction. But for the power Doppler, the power Doppler is pretty sensitive to a small vessel with a small velocity, because in this case, we only want to see the topology of the small vessels. We don't really need to know the velocity magnitude and the direction. Different from the color and the power Doppler, spatial Doppler actually is doing a time frequency analysis. Spatial Doppler provide the velocity distribution as a function of time. There are two spatial Doppler. One is a continuous wave Doppler. We call the CW Doppler. Basically, only the velocity distribution along this line can be detected as a function of time. On the other hand, we have a pulse wave Doppler. We can localize the gates at a certain depth to estimate the velocity distribution as a function of time. So one of the good things in my lab using the research platform is we can scan the color the color Doppler. We can obtain the color Doppler and the BMO in the ready mode. So here shows the example of the cardiac and the carotid artery imaging in my research platform. Okay, so to overcome the limitation of a conventional color Doppler, which can only provide the one-dimensional velocity component estimation, modern commercial machines already provided the vector flow imaging. There are three companies doing vector flow imaging. One is MyRay, called VFlow. The other one is VK Medical. The next one is GE. It's called broad spectral imaging. So the principle for the MyRay VFlow is based on the multi-angle beams. If we can generate a different angle beams and estimate the velocity along this beam, then we can combine all these angles to produce the final velocity vector. So this is still based on Doppler, but we leverage different angles to obtain the final velocity vector. On the other hand, the VK and Medical uses a different approach. They use the transverse oscillation. The idea is they want to generate the oscillation or carrier or frequency along the lateral direction. Then they can leverage the Doppler effect to estimate the phase shift or Doppler shift along the lateral direction. GE use a different approach. They use the speckle-tracking, which I will introduce later. They for the speckle-tracking, they can do a approximation between the two frames and estimate the motion between the displacement between the two frames. For the visualization, what you see here is there are two different types of visualization. One is the trajectory visualization. What you see in the MyRay system, you can see you can really trace the trajectory of the particles inside the vessel. For the VK Medical, they use the fixed arrow. So you can see the direction of arrow to know the flow direction, but you cannot see the trace. You cannot really trace the particle trajectories. For the GE, they also use the trajectory visualization. For all these systems, they kind of leverage the ultrafast imaging, which we will introduce later. For the ultrafast imaging, they use a multi-angle plane wave to increase the frame rate to 1 kilohertz. So in this case, they can use a very high frame rate to visualize very detailed hemodynamics in the vessel. I want to introduce some ultrafast imaging, the principle of ultrafast imaging using a multi-angle plane wave. If we compare to the conventional focus beam, for the focus beam, we generate a bunch of focus beam and do a line-by-line scan across the image region. So the frame rate is quite limited. The other strategy is doing to increase the frame rate is doing the plane wave imaging. In this case, we don't do a focus beam in the transmission. We use a one angle plane wave or zero angle plane wave to do an image. The image quality is quite poor, right? If we increase the multi-angle plane wave and combine this multi-angle plane wave imaging, we can get a finer image resolution. In this case, you can see if we use a 17 angle plane wave, we can get a very similar image quality as a similar quality for the conventional focus beam, but we can increase the frame rate as high as 1 kilohertz. So my question is why is the current VFI image is good enough? We know the current VFI image using the multi-beam or speckle-tracking or lateral acceleration, but we don't know which one is better, right? The second question is how if we want to see a more detailed hemodynamics, we need to increase the frame rate as high as possible. But the frame rate is depending on the number of angles you use in the plane wave imaging. For the microwave approach, they use a multi-angle plane wave imaging and the Doppler to estimate the vector flow. But the drawback is they're still based on the Doppler principle. They use the autocorrelation estimator to estimate the mean frequency. It's still based on Doppler principle. The drawback is this kind of autocorrelation function is a bias. It's bias estimation. So the velocity is underestimated. And the variance of velocity estimation is highly depending on the ensemble size you use. Usually we use 8 to 12 samples to estimate the velocity. So in this case, if you use more samples, you can reduce your variance, but your frame rate is also reduced as well. We know the Doppler estimator has a problem of spatial aliasing, which means we cannot estimate a very high speed bar flow. The next problem is the visualization. We see trajectory base or fixed error base has been implemented in the machine, but we don't know which one is better. And is it robust enough? As we point out, the Doppler estimator has a problem of bias, right? So if we want to trace this particle, we probably can will accumulate errors and maybe the trace is not correct, right? So it's not robust enough. So there is a clinical need to develop ultrafast imaging and robust velocity estimator and robust particle trajectory imaging. Our solution is to develop ultrafast VFI based on speckle-tracking. We use fewer plane wave imaging angles. We use 3 to 5 angles to do ultrafast imaging. We also estimate the velocity vector based on the different angles. But here we use a speckle-tracking to estimate axial velocity and then combine all the axial velocity component for different plane waves to produce the final velocity vector. We also develop a robust superposition-like particle imaging. In this case, because the speckle-tracking can provide the speckle similarity, which can use as a quality index, so we can know this estimation is reliable or not. This helps us to trace the trajectory of the flow. Okay, so I think I can, yeah, there's a audience poll, so I can wait a little bit.
Yes, perfect. Thank you so much, Dr. Yang, for a really fascinating presentation so far. The images and videos really look amazing. So we're going to take a quick break here just to ask the audience a couple of questions to get to know a little bit more about the research that you're doing. The first question that we'd like to ask is, do you currently use a research or engineering ultrasound system? And you have a couple of options there. And the second question we would like to ask is, do you currently use vector flow imaging or any related techniques in your research? And you can check all the boxes that apply. And for the last question is, would you be interested in learning more about this research that we're presenting today or about the Prodigy system? And we'll just give everyone a minute or two to answer those. Okay, so it looks like we have a lot of users here that are using a different commercially available system, which is great to hear. And also a lot of users who are either using VFI or studying another form of ultrasound plane wave. So that's perfect. So thank you so much for sharing your thoughts and telling us a little bit more about yourself. And now we will return things to Dr. Yang to go through the remainder of the presentation.
Okay, good. Yeah. Okay, so because my method is based on the speckle tracking, let me introduce some basic principle of speckle tracking. So this is an example showing you the flow, right? Blood flow vessel. For the speckle tracking, we actually do interference displacement estimation between the two frames. So one is a reference frame, the other one is a target frame. So we can pick up the kernel, which is used to estimate the one velocity inside the kernel. In the target frame, we can define a search region, right? This search region can depend on your applications. So for the very high dynamics, for maybe the search region should be large enough. For the slow flow, you can narrow your search region. So you can do a full search inside the search region, right? And then you can find the best match for this kernel. And then you can get the two dimensional displacement components. So one is axial component, right? So we can obtain the axial displacement divided by the time between the two frames. So finally we can get the axial velocity, right? For the lateral velocity, we do the same thing. Here you can see the axial velocity much better than the lateral velocity. So this is because the nature of the ultrasound beam. In the ultrasound beam, the lateral resolution is much lower than the axial resolution. That's why the axial velocity is more accurate than the lateral velocity. Well, one of the good things for the speckle tracking is they provide the correlation map, because for this correlation, we use this correlation to do a matching, right? So this correlation can tell us the quality index. If the correlation is low, well, we can choose not to trust this estimate. I want to point out for the speckle tracking, we only need to do is two frames, right? We only can use the two frames to produce one velocity estimate. But for the Doppler, for the autocorrelation estimator, we need a bunch of samples. For example, 8 to 16 samples to get one velocity estimates. This means that for the speckle tracking, we can get a very high frame rate compared to the conventional Doppler estimate. This is our proposed method, which we call LSST. We use the three-angle plane waves to generate three different plane waves to estimate the velocity, axial velocity component along each angle. And then we do scan conversion from the tiered frame to the rectangular frame. And then we combine these three axial velocities to produce the final velocity vector. Here we use this square, right? But we can use a cross correlation map that I show in the next slide as a quality index to regularize the estimation results. Here I want to give you some mathematics for the For the unknowns, we have two unknowns, right? One is lateral velocity. The other one is axial velocity. We have three measurements coming from the three different angles. We have angle one with axial velocity, angle two, axial velocity, angle three. So we have three equations to solve the two unknowns. So this is over-determined equation. We can use the least square to solve this equation. But as I mentioned earlier, for the speckle tracking, the minimal samples we need is just 2 friends. But in case if we want to get more reliable result, we can increase the friends. So for example, if we use the 10 friends, we have 9 interfriend estimates. So we can use all these estimates to make this matrix more bigger, right? And can get a more reliable result. Here we include the correlation coefficient as a weighting into the least square to regularize the final result. Okay, let me show you some simulation result using FEAR 2. I think FEAR 2 is very familiar with, is very popular in this area. For the simulation, ultrasound simulation, they always use FEAR 2 as a simulator. Here I simulate the laminar flow to mimic the practical flow pattern inside the vessel. The plane wave I use has 3 angles. The PRF is 10 kilohertz, which means the effective frame rate is 10 divided by 3 is 3.3 kilohertz. It's pretty high. Here is the simulation result at the Doppler angle is 16-degree Doppler angle. I compare 3 different methods. The first one, this one is a conventional speckle tracking. The bottom one is our proposed method. We also replace the speckle tracking by the conventional autocorrelation. We call the ACF, autocorrelation function. We want to compare these 3 to know to know if our performance is good, is better than other ones. So here, this image is showing the vector flow result. Because this is simulation and we have a laminar flow inside the vessel, we can see the flow is much higher in the center it's much higher in the center, right? So if we just look at the result, you can see the LSST is much better than the other approaches. If we just look at the one scan line in the center, so we expect that we can see the laminar flow profile. So you can see all the 3 methods can do a good job in estimating the axial velocity. The axial velocity is good, but the lateral velocity is not good for conventional speckle tracking and the LS-SCF, which is based on the Doppler estimator. Our method can do a decent job to obtain the lateral velocity. It's a little bit underestimated, but still very close to a true profile. Okay, so here I want to show you our developed new particle flow imaging. The idea is we pick up the larger intensities of speckle inside the vessel at the initial points, and then we trace these points as a function of time by accumulating the interference displacement between the different particles. So on the right, on the left is a ground truth. On the right is our method. So in the middle is a conventional Doppler estimator, What you see here is our method is very close to the ground truth, right? So the conventional Doppler estimator has a large error because the lateral velocity is not good. So the particle trajectory image is not good as well. We also conducted in vitro experiments to verify our method. We use a Prodigy research platform and flow phantom to investigate the two vessels inside the phantom. One is 90 degrees, very challenging for vector flow to estimate. The other one is 55 degrees. It's also change as well because it's deeper. Well, so we use a different center frequency for different vessels. We also use a different plane wave angles to know the effect of the number of plane waves. One of the good things for our research is we use a research platform Prodigy to do pulse sequence design. It's much easier for us to design our own pulse sequence because, as you see, the interface is so easy. What we need to do is to input the number of the parameter we need. So in this case, we designed the three-angle plane waves using this user interface. The other good things for research platform is we can combine our develop algorithm into the Python interface. So right now, the Prodigy already provided the Python interface, which means you can write your code with the Python, and you can access the data from the computer memory, and you can run the program in real time, depending on your platform, right? So we can implement our algorithms using the Python, and we can see the real-time imaging. So let me show you the phantom result. We compare the arrow-based VFI and the new particle imaging. So on the top, this is the arrow-based VFI. So our method is LSST. As a counterpart, we compare LS-SCF, which is based on the Doppler principle. On the bottom, we have new particle imaging. So you can see the LSST is the estimation is very stable because in this case, we generate a constant flow. It's not a pulse type flow. So we expect the flow is very static. It's very static. It's very static. It's not dynamic as with time. So we can see the LSST can get a more reliable result than the LS-SCF. If we look at the more deeper vessel here, right, we can see the difference between the two methods. For the LS-ST, we can see the result is more reliable than the LS-SCF. For the new particle imaging, we can also see the very nice visualization. We also conducted the human experiments with the Prodigy research platform. We scan carotid artery. We use a very similar parameters with the phantom study. But in this case, we use more larger angles, but we still limited to three plane waves angles. Here is a carotid artery result. We show the result using the arrow-based VFI. On the left, we show the pulse wave Doppler. So you can see this is 1 second. So we kind of slow down the movie to see the dynamics of the flow. So on the right, we compare 4 different methods. This one is a conventional color Doppler with the angle correction. Because we know the angle, right? So we can detect the angle from the imaging. We we correct this angle to get the vector velocity vector along this ball. The other one is a conventional speckle tracking, LS-SDF, LS-ST. So you can see if you just look at the imaging, so you can see the LS is more reliable than other images. For example, if you see the color Doppler with angle correction, you can see some artifacts here, right? If you see the LS-SCF, you can also see the artifact here. For the LS-ST is much more reliable than other methods. We also display the new particle imaging using the LS-ST. On the left is the new particle imaging using LS-ST compared to the L-based VFI. So in this case, you can see for the new particle imaging, you really see the trace of the particles, right? You can see the very detailed dynamics inside the vessel. On the other hand, for the arrow-based, you cannot really see the dynamics inside the vessel. This can explain why the trajectory, like the new particle imaging, is a good tool to visualize hemodynamics of the flow. I want to mention the other applications regarding vector flow imaging. In my lab, we also conducted blood pressure. The idea is we estimate the diameter of the vessel and the blood flow and the vector flow inside the vessel. We combine the two different measurements to get the blood pressure. This is very promising because we can simultaneously estimate the diameter waveform and the blood flow imaging. We also use a prodigy to do the experiment. So this kind of research program allows us to do a very broad application of the ultrasound applications. So I want to summarize my talk today. What you need to know in this talk is the conventional Doppler imaging only detects a one-dimensional velocity component. VFI enables the visualization of the vector velocity vector using a trajectory or arrow-based approach. But we know a trajectory visualization is much better than the arrow-based. Ultrafast imaging and the VFI can provide more hemodynamics information because of high frame rate. Speckle-tracking-based VFI is promising compared to the Doppler-based in terms of estimation errors. Prodigy array system facilitates our integration of pulse sequence and develop algorithms for this kind of advanced analysis. Thank you for your attention.
Thank you so much, Dr. Yang, for that great talk. It was very informative, and I know I learned a lot from it. So we will now be moving into the Q&A. Just a reminder, there is a Q&A dialog box if you wanted to type out the questions and so that Dr. Yang can answer them, whether about the prodigy or about the research, or if you have any questions about your own research. Or if you wanted to also come off mic and ask a question.
Yeah.
And while we're waiting, in case anyone is typing, I did have a question, Dr. Yang.
Yeah.
I was just wondering, because I saw you had in vivo experiments in your research, and then you also performed some clinical experiments with the system. So I was curious, what would it take? Because we know getting systems into the clinic, like FDA approval, certifications takes a while. How far away is the clinical translation for this prodigy? Are we talking maybe a couple of years? Is it possible now with the right approvals?
Understand. Yeah, this is a good question. I think for the research platform, we have a many research platform in the market, right? So Prodigy is one. The other one is Versonics, and we have I think the other one is coming from the Poland, right? But for research platform, I think the the advantage is you can modify your power sequence. Yeah, you can design your own power sequence, but it's not the clinical machine, right? But I think for the Prodigy research platform in my lab, we can conduct the human experiment because we have our IRB being approved. So I think if we want to do a human scan using the Prodigy, I think it is not really a problem because in my case, the IRB is not difficult to get. For the Prodigy, if we want to become the clinical machine, I think the FDA, something, certification is required. But I think it's a time, it's time problem. In my case, IRB is not a problem. I think for this kind of a certification is not difficult to get. It's depending on the company strategy.
Definitely. Thank you for clarifying that. I know that's usually on everyone's mind, which is clinical translation. We have one question actually while you're on that slide from Vahid, who's asking, can you explain more about the LS and ST method?
Okay, so I think it's for the LSST. So if we just look at these words, there are two words, right? LS. LS means this is square. ST means speckle tracking. So the idea is we use the speckle tracking to estimate the axial velocity component. And then we use this square to combine this axial velocity component from the different wave angles to get the final velocity vector. Because for the velocity vector, what we need to know is the vector is two velocity component. One is axial, right? The other one is lateral. But we don't know the lateral, but we actually can use a different angle to get the different component. So the idea is we combine this velocity components at the different angles to produce the final velocity vector.
Perfect. Thank you so much for clarifying that. And we have another question from Anil, who's asking, what are the limits to the spatial and temporal resolution that can be achieved with a Prodigy? And if someone is interested in microcirculation, for example, in kidneys or cardiac, is that possible?
Okay, so for the spatial resolution, it depends on the kernel you select in the speckle tracking, right? So, but this is a trade-off. If you want to have a higher spatial resolution, your velocity estimation will degrade. So this is a trade-off. For the temporal resolution, I think for the conventional VFI, they mostly use Doppler. For the Doppler, they need to use 8 to 16 samples. So the temporal resolution is depending on the number of samples used. For the speckle tracking, in principle, you can only use the 2 samples to get the one velocity. So I expect the speckle tracking based VFI has higher temporal resolution than the Doppler. For the microcirculation estimation, I think it's very challenging. Yeah, even for the conventional Doppler, it's challenging as well. So if you look at the commercial machine for the MyRay, for GE and BK Medical, they usually visualize the bigger vessels. They don't visualize the small vessels. But I think it is challenging. It's very challenging.
Perfect. Thank you for answering that one. And we have another question from Marco, who's Marco's saying that currently they're using 2D autocorrelation to estimate muscle tissue velocity and detecting single motor unit tissue displacements. So he's wondering, right now they're estimating axial velocity. And do you think that with the LS and ST method with multiple angles can be used to estimate the velocity vector of the muscle tissue?
Yeah, sure. Because if we use a plane wave, multi-angle plane wave, you can generate the plane wave with the different angles. So you can estimate the axial velocity component along this angle, right? So basically, I think you also can get the velocity vector. So this is not only for blood vessel, right? It can be applied to the myocardial muscle tissue. I think yeah, this is doable. Yeah.
Perfect. Thank you. Do anyone else in the audience have any last minute questions? We have about just under 10 minutes left if anyone else wants to type a question into the chat. And while we wait, actually, Dr. Yang, I had another question. I was curious about contrast imaging with the Prodigy. And kind of tying back to the microcirculation question, how are the advancements with contrast imaging, and would that allow you to get better sensitivity?
Yes, I think so. Because for the contrast imaging, I think for the microcirculation imaging can benefit from the contrast agent. I'm not the contrast agent guy, so I don't know. I don't know if I have no imaging contrast imaging in my hard disk. But I think it's also doable for Prodigy to conduct the contrast imaging. But I think I expect the contrast imaging can benefit can get a better VFI imaging. So right now I think the other one of the popular research is regarding the super resolution imaging. They leverage the contrast agents to localize the particle inside the microvascular. So I think yeah, Prodigy is doable for this application.
Yeah, I know there's also a lot with photoacoustics being developed right now. But I don't think that would, correct me if I'm wrong, that wouldn't really be for microvascular imaging or disease, or could you do that?
Yeah, I do. I do photoacoustic imaging, right? But for the microvasal imaging using the photoacoustic, I think they leverage the we call the optical resolution photoacoustic imaging. So it's yeah, you can get the higher resolution. Very high resolution than the conventional ultrasound to visualize the result. Yeah.
Perfect. Well, we don't have any other questions in the chat. I can wait another minute or two if anything comes in, but we have reached the end of today's session. And just to be cognizant of everyone's time, I just wanted to mention some last minute housekeeping. So as mentioned at the start of the webinar, we will answer any outstanding questions if you think of any right now and you just want to type them into the chat box, and then we will get back to you with an answer. We'd also really like to thank Dr. Yang for his presentation today and as for taking the time to address many of the questions. I know you're in a very far away time zone right now and it's late in the evening for you. So thank you so much for taking the time to be here. I trust that we have been able to provide you with some relevant information for everyone attending regarding the studies, and hopefully you will be able to take this information back to your own labs. In the coming days and weeks, if you have any further questions about the work that was discussed today, or questions about the Prodigy system or any of the equipment at Cintiqa, we encourage you to reach out to Cintiqa through our website or our online forums, and we would be happy to discuss further. We would also welcome the opportunity to discuss your specific research goals. If you wanted to discuss how our equipment can be incorporated into your own research and how it can advance further. Thank you again for everyone for taking the time to attend our session, and we look forward to seeing you at the next Cintiqa event. And have a great evening or morning or afternoon, depending on where you are.
Thank you.